everybody, and welcome to G-Tech. After my last episode, I connected the amplifier to my variac and incandescent current limiter. I found a high DC offset on the right channel. I recorded the whole troubleshooting process. Unfortunately, I lost that footage. I apologize for that. But you can see similar troubleshooting on prior episodes that I made last year. Basically, what I found were two transistors and a faulty diode on the control board. Now, we're going to power that amp up again, and if there's no DC offset, we're going to set the bias and we're going to put that amp to the test. If you like these videos, please hit the like and the subscribe button. It'd be much appreciated. Well, let's get to it.
Warning: do not attempt this project unless you are experienced with electrical circuits. Serious injury, property damage, and even death can occur with this wire.
Now let's check that DC offset voltage again. Okay, we have 37 millivolts on the left channel and we have 13 millivolts on the right channel. We're good to go. I warmed up the amplifier by running it into my dummy loads. Now we can set the bias. The service manual specifies a bias setting between 300 and 400 millivolts, so we'll aim for the midpoint, 350 millivolts. The left channel is a little high, so let's bring it down to 350 millivolts. Now let's check the right channel. It's a little low, so we'll bring it up slightly. $354 millivolts. Good enough. Next, let's feed the amplifier a 1 kHz test tone, drive it into our dummy loads, and see where it begins to clip. As you can see on the Fluke 177 meters, the amplifier clips at approximately 45 volts RMS into an 8 ohm load. That works out to about 250 watts per channel. Now, let's verify that measurement and check the amplifier's other specifications using my QuantAsylum QA403. To do that safely, we need to attenuate the amplifier's outputs because the maximum input voltage of the QA403 is 40 volts. I built a 6 decibel attenuator using a 1 k ohm series resistor and a 1 k ohm shunt resistor to ground. I only had 1 watt resistors available and I needed greater power handling, so I used 4 1 k ohm resistors in a series parallel arrangement. This maintains the required 1 k ohm resistance while increasing the power handling capacity. Now that everything is connected, let's look at power and distortion. Once again, we'll use a 1 kHz test tone. First, let's measure distortion at the amplifier's rated power. Here we have 0.03% distortion at the rated output of 200 watts RMS per channel, with both channels driven. Moving on to power at clipping, we again measure approximately 45 volts RMS. We're at the knee of the distortion curve with approximately 1% distortion at 250 watts RMS a channel, both channels driven. Now let's look at the frequency response of the left channel. The readings near the lower left corner of the screen show the response from 5 Hz to 20 kHz. At 20 kHz, the left channel is down only 0.27 dB. Now let's check the right channel. Again, from 5 Hz to 20 kHz, the response is nearly flat. At 20 kHz, the right channel is down 0.3 dB. Finally, let's measure the noise performance. With both amplifier inputs shorted, we measure 182 microvolts of noise on the left channel and 135 microvolts on the right. At the rated output of approximately 200 watts per channel, the output voltage is 40 volts RMS. Dividing that voltage by each noise measurement and converting the ratios to decibels gives us a signal-to-noise ratio of approximately 106.8 dB for the left channel and 109.4 dB for the right channel. Overall, the amplifier achieves a signal-to-noise ratio of better than 106 decibels. Here's my wife pointing out the amplifier's measured performance. At the rated output of 201 watts RMS per channel, with both channels driven, distortion measures just 0.03%. Into 8 ohms, the amplifier produces 250 watts RMS per channel at 1% distortion with both channels driven. Into 4 ohms, it produces 350 watts RMS per channel at 1% distortion, again with both channels driven. The frequency response extends from 5 Hz to 20 kHz, the response down only 0.3 dB at 20 kHz. And finally, the signal-to-noise ratio is better than 106 dB. Impressive, isn't it? I want to thank Lee Laatsch for sending me the driver transistors for this amplifier. We still have a few cosmetic issues to address. We have a bent faceplate, loose VU meters, and someone installed substandard lighting behind those meters. We'll fix all that on the next episode, and then we'll do a listening test for that amplifier. Thank you for watching, and we'll see you on the next episode. It's a wrap.